Welcome to Elementary Functions. Today we're going to talk about the double angle and the half angle identities. My name is Wendy Fresh. I'm from Portland Community College and this is Math 112. Before we talk about the double angle and the half angle identity, let's review the summary of the sum and difference identities. The sum and difference identity for the cosine function, the sum and difference identity for the sine function, and the sum and difference identity for the tangent function. You should make sure that you've got this page printed or easy access to so that we can use it to establish the double angle and the half angle identity that are following. Let's begin with the double angle identity. To establish these identities, the identities that have been learned in previous sections will be used. So let's start with the double angle identity for the sine function. The sine of 2 theta is equal to, so we're going to take what we already know and try and develop this identity. And what I know is that having 2 thetas is the same thing as having a theta plus a theta. And by writing it like this, I can use the sum identity for the sine function to say that the sine of theta plus theta is the same thing as the sine of theta times the cosine of theta plus the cosine of theta times the sine of theta. Now, if you're confused about where I got that second line from, pull out the identity sheet from the previous page and take a look at what the sum identity is for the sine function. Now, even though these terms look different, the commutative property tells us that sine theta cosine theta is the same thing as cosine theta sine theta. So they actually are the same thing. And so I'm going to say that this is equal to 2 times the sine of theta times the cosine of theta. One way of thinking of that is that I have one sine of theta cosine theta and I have another one. So altogether I have 2. So that is my double angle identity for the sine function. I'm going to use the same method for the cosine function. I'm going to say that the cosine of 2 theta is equal to the cosine of theta plus theta. And I'm going to use my identity sheet from the previous slide to say that this is equal to the cosine of theta times the cosine of theta minus the sine of theta times the sine of theta. And cosine of theta times the cosine of theta is the same thing as cosine squared theta. And sine of theta times sine of theta is sine squared theta. So that is a double angle identity for the cosine function. We can use the Pythagorean identity and the identity for the cosine above to express the following. So there are 2 other ways of writing the double angle identity for the cosine. And if you notice in both of these examples, I start with the identity that we just came up with, that the cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Now I suggest that we use the Pythagorean identity. Remember that the Pythagorean identity says cosine squared theta plus sine squared theta is equal to 1. So what I'm going to do in this first one is I'm going to rewrite cosine squared theta as 1 minus sine squared theta. And if I do that and then subtract the sine squared theta that was already there, I end up with another way of writing the sum identity for the cosine. Now you might be wondering to yourself, I don't know why I would ever want to do that. Well, in a problem where you only know information about sine of theta and you don't know anything about cosine of theta, even though you might be able to find out something about cosine of theta, this would be a more direct way of getting an answer. Now, the third one is going to be doing exactly the same thing, only instead of rewriting the cosine like I did in the previous, I'm going to rewrite sine. So I end up with cosine squared theta minus, now I'm going to put parentheses here because I have to make sure that I subtract the whole thing. Sine squared theta is the same thing as 1 minus cosine squared theta. And when I distribute that negative through, I end up with, looks like 2 cosine squared thetas minus 1. All right, so when that distributes through, the minus here converts that minus into a plus. So we now have 4 double angle identities for sine and cosine. The first one is for the sine of 2 theta, and that's equal to 2 times the sine of theta times the cosine of theta. And then we have 3 variations of cosine of 2 theta. We can either say that's equal to cosine squared theta minus sine squared theta, or 1 minus 2 times sine squared theta, or 2 cosine squared theta minus 1. And we're going to use those identities in example 1, which says if cosine theta is equal to negative 2/5 and theta is between pi and 3 pi over 2, find the exact value of sine of 2 theta is the first one, and we have only one option for the sine of 2 theta. That has to be 2 times the sine of theta times the cosine of theta. And before I go any further, let's just talk about theta. They said that theta was between pi and 3 pi over 2, so I'm just going to write up here that that tells me something. It tells me I'm in quadrant 3. All right, so 2 times, what is the sine of theta? Do I know what the sine of theta is? I don't think I do, but I think I can figure it out. I'm being given that the cosine of theta is negative 2/5, so I'm going to use the Pythagorean identity to find what the sine of theta is equal to. I'm going to input that negative 2/5 for cosine of theta. And I'm going to solve. Let's see, I get sine squared theta is equal to 1 minus 4 over 25, which is going to be 25 over 25 minus 4 over 25, or 21 over 25. So taking the square root of each side, I'll get plus or minus the square root of 21 over 5. And to determine whether it's plus or minus, I have to go back to the fact that I'm in the third quadrant, and that tells me that my sign is negative. So I'm going to input negative root 21 over 5 for my sine, and then for my cosine, negative 2/5. And if I multiply all those together, I get 4 root 21 over 25. That's what the sine of 2 theta is equal to. All right, now let's take a look at the cosine of 2 theta. And in order to do the cosine of 2 theta, I either need to know something about sine squared theta or cosine squared theta, or both. And in this case, I actually do know something about both. I don't know about sine squared or cosine squared, but I know about sine of theta and cosine of theta. So I could really use any 3 of these identities. What I would suggest, though, is that if you're given the option, that you always pick the option of the angle that was given to you. In other words, I was given that cosine of theta is equal to negative 2/5, so I know that that is true. In the event that I have made a mistake in determining what the sine of theta is, that mistake would just simply carry over into my cosine of 2 theta, and I don't want that to happen. So I'm going to use the formula that says 2 times cosine squared theta minus 1. And I'm going to take the cosine as negative 2/5 and substitute it in and simplify. That gives me 2 times 4 over 25 minus 1, or 8 over 25 minus 25 over 25, which is negative 7/25. All right, now let's talk about the double angle identity for the tangent function. We will use the sum identity for the tangent function to establish the double angle identity for the tangent function. So just like you saw us do on the previous slides, I'm going to rewrite the tangent of 2 theta as the tangent of theta plus theta. And it might help if we have this identity that we established in the last video. we know that the sum identity for the tangent function is equal to the tangent of one of the angles, so ours is theta, plus the tangent of the other angle, also theta, and the whole thing over 1 minus the tangent of theta times, in this case, theta. And tangent of theta plus tangent of theta is simply 2 tangent of theta. And in my denominator, I end up with 1 minus tangent squared theta.